Ad hoc networks are defined as a category of wireless networks that utilize multi-hop radio relaying and are capable of operating without the support of any fixed infrastructure. The nodes in ad hoc networks share a common broadcast radio channel, and the bandwidth that is available for communication is limited as the radio spectrum is also limited. So in this case, the care has to be taken that all the nodes that receive or transmit the data will have a fair share of bandwidth that is available, and resulting to which the utilization of the bandwidth will be very efficient. So there are certain problems that are generally shared by wireless medium. The problems can be like hidden and exposed terminal problems, or limited bandwidth availability because of the mobility of the nodes. So these all can be the problems that generally arise. And these kind of problems are not generally observed in the case of wired networks. So a different set of protocols is required for controlling access to the shared medium in wireless networks. So above all these, there are certain issues that are involved while a MAC protocol is being designed for ad hoc networks, and that will be discussed. So the listed all are the issues that are to be taken into consideration while designing a MAC protocol. Among them, the first and the most important one is about the bandwidth. So as the spectrum that is available is very limited, the bandwidth that is available is also limited, and the protocol that is being designed for this particular ad hoc networks, it must be such that the bandwidth is efficiently utilized. The bandwidth can be made utilized efficiently. And the second parameter that has to be strictly concerned over is about quality of service. Providing the quality of service parameter is very difficult when the nodes are mobile, and especially this happens very difficult with respect to ad hoc networks. So bandwidth reservation made at one point of time may be invalid at another point of time. So quality of service is necessary for some time critical traffic scenarios. For example, when military applications are considered, so there the time actually plays a very important role. And the third point is about the synchronization. Exchange of control packets is required to achieve or to have some sort of synchronization with respect to the time between the nodes that are present in the network. And here care must be taken that the control packets do not consume too much bandwidth in the network. So if the entire bandwidth is occupied by the control packets itself, there will not be much availability of the bandwidth for the actual data to be transmitted. And then comes the problem about the hidden and exposed terminal problems. So here you have two problems that are visible here. The first one is hidden terminal problem, and second one is exposed terminal problem. So coming to the hidden terminal problem, so this particular problem is very unique in the wireless networks. Hidden terminal problem is replicated to the collision of packets at the receiving node due to the transmission of the data from nodes that are not in the transmission range, but they are in the range of the receiver. So collision happens when both the nodes that are transmitting the data at the same time without knowing about each other. They will not be having knowledge about one another, but simply will transmit the data. And the second problem that is here is about exposed terminal problem. So exposed terminal problem. This is about the inability of a node to transmit data to some other node. So the inability can be because that the node might have got blocked due to the transmission by the because of the transmitting node. And the next problem that is present here is another thing is, when we are speaking about the hidden and exposed terminal problems, there is a chance that these two problems will reduce the throughput in the network significantly when there is a huge traffic within the network. So the next problem what you have here is exposed prone shared broadcast channel. So the broadcast nature of the radio channel is another important factor to be considered for the design of a MAC protocol. When a node is receiving the data, apart from the sender, no other node that is present in the network must start transmission of the data. And nodes should get access to the shared medium only when its transmission do not affect the ongoing process of transmission. And there is also a chance that multiple nodes can contend the same channel at the same time, and then there may exist a possibility of collision. So Whatever may be the protocol that you are designing, that protocol, it must be designed in such a way that a grant should be given to the nodes to access the channels such that the collisions are minimized. Equal priority must be given to all the nodes that are present in the channel. And the next important issue that has to be considered here is the distributed nature or lack of central coordination. In particular, about when you are speaking about ad hoc networks, a centralized coordination does not exist in the ad hoc networks. All the nodes that are present in the network will keep on moving. Therefore, the nodes must be scheduled in a distributed manner to make them gain access to the channel. To ensure this exchange of the control information, um, some sort of control information is required here. And the last parameter is about the mobility of nodes. So this is a very important factor again that will affect the performance of the system or the network. So when you are saying that the nodes are moving or when the nodes are highly mobile, so the bandwidth reservations, the control information that is being exchanged can be of no use. So at this particular junction, the protocol being designed must consider this mobility factor such that the performance of the system will not be disturbed due to the mobility of nodes. So the figure that is in front of you is the best example that can be taken into consideration to explain the hidden and exposed terminal problems. So let me first explain what a hidden terminal problem is. So we have few nodes here. So consider you have two nodes S1 and S2 that wish to transmit data to R1 at the same time. Then what happens? The packet collided R1. So because S1 and S2 are hidden from each other, as they are not within the direct transmission range of each other, they do not know the presence of one another, because of which the hidden terminal problem can arise. Now coming to the concept of the exposed terminal problem. So again consider the nodes. If transmission from node S1 to another node R1 is going on, and node S3 cannot transmit the data to node R2 because it takes for granted that the neighboring node S1 is in transmission and it feels that it should not interfere with the ongoing transmission. So this is all about the hidden and exposed terminal problems. MAC protocols for ad hoc wireless networks can be classified into several categories depending upon different criteria like the initiation approach, the time synchronization and reservation approaches. But here in the case of ad hoc networks, when MAC protocols are to be classified, and the classification is made depending upon three basic types. The first one is contention based protocols, second one contention based protocols with reservation mechanisms, and the third one is contention based protocol with scheduling mechanisms. The term contention actually means opinion. So these contention based protocols, the first category what we have, these will follow the contention based channel access policy. So every node does not make any resource reservation as a prime consideration. Whenever the node receives a packet to be transmitted, it will contend with its neighboring node for access to the shared channel. So contention based protocols will not provide quality of service to the sessions, as the nodes will not be given a regular access to the channel. So these contention based protocols are again categorized into two varieties. They are the sender initiated protocols and the receiver initiated protocols. The sender initiated protocols are again categorized into two varieties: single channel sender initiated protocols and multi-channel sender initiated protocols. So the single channel, let me first explain about the sender initiated protocols. So the packet transmissions, whichever may be the node that is willing to transmit the data, the packet transmissions from that node are initiated by the sender node. And similarly, in the case of receiver initiated protocols, the receiver node will initiate the contention resolution protocol. Now coming to the single channel sender initiation, in these particular protocols, the total available bandwidth is used as it is without being divided. So a node that wins the contention to the channel will make use of the entire bandwidth in order to transmit the data. So whereas in the case of multi-channel sender initiated protocols, in the available bandwidth is divided into multiple channels initially. So because of doing this, several nodes will be made enabled simultaneously to transmit the data. Each of the node that is being made to transmit the data will make use of a separate channel. The next category of the protocols is the contention based protocols with the reservation mechanism. So ad hoc networks sometimes may need to support for the real-time traffic, and this particular utilization or bringing into scene the real-time traffic will need an assurance of quality of service maintenance. And the contention based protocols, in these contention based protocols, nodes are not guaranteed with periodic access to the channel, so they might not be in a position to support the real-time traffic. So in order to make the protocols support real-time traffic, certain protocols will have mechanism for reservation of the bandwidth as a priority initially. So such protocols which are initially taken bandwidth into consideration will provide quality of service support to the time sensitive traffic sessions. So the protocols under this particular criteria are again divided into two types: synchronous protocols and asynchronous protocols. So the synchronous protocols, they require the time synchronization among all the nodes that are present in a network, so that the reservations made by the node are known to another nodes in the neighborhood. Global time synchronization is generally difficult to achieve. And coming to the asynchronous protocols, these protocols will not require any sort of global synchronization among all the nodes that are present in the network. And these protocols will usually use relative time information for effective reservation mechanisms. So coming to the classification, in detail classification of MAC protocols for ad hoc networks. The MAC protocols for ad hoc networks are categorized into four. So contention based protocols with reservation mechanism, contention based protocols with scheduling mechanisms, and other MAC protocols are defined. Again, the contention based protocols are classified into two varieties: sender initiated protocols and the receiver initiated protocols. The sender initiated protocols are subclassified into single channel protocols and multi-channel protocols. So each of those given below are the examples of the protocols that are stated above. The contention based protocols with reservation mechanism is classified into the synchronous and asynchronous protocols. And the remaining all are the examples of the protocols that are listed. The first protocol that was introduced under the contention-based protocols is MACA protocol. MACA stands for Multiple Access Collision Avoidance, and this was a protocol introduced in around 1990s. So this is a protocol that came into scene taking into consideration the disadvantage that existed in CSMA. So in CSMA protocol, the sender will first send the channel for the carrier signal. If the carrier is present at that particular instant of time, it retries after a random period of time. Otherwise, it will transmit the packet. So CSMA technique that was there, it senses the state of the channel only at the transmitter. And the main disadvantage of this protocol is it does not overcome the hidden terminal problem. And the bandwidth utilization of CSMA protocol is very less because of the exposed terminal problem that usually existed earlier. So MECA will not make use of the carrier sensing for the channel access. Apart from that, it makes use of two additional signal packets being called as RTS and CTS, which stands for ready to send, request to send, and clear to send. And whenever if the packet is transmitted by a node is lost, then that particular node will use a special algorithm called as binary exponential backoff algorithm, BEB algorithm, to back off for a random interval of time before trying again to transmit the data. And in this particular BEB algorithm, each time a collision is detected, the node which wishes to transmit the data will double its maximum backoff window. So the diagram will present the packet transmission in MACA protocol. Here, by looking at the diagram, it can be clearly understood that the neighboring nodes near the sender that will hear the RTS packet do not transmit for a long enough period of time so that the sender could receive CTS packet. And the second point here is both the RTS and CTS packets, request to send, ready to send, and clear to send packets carry the expected duration of the data in the packet transmission. As seen in the diagram, when the sender wishes to transmit the data to one particular receiver, it will be transmitting RTS packets to all the nodes that are present in its surroundings. such that all the neighboring nodes will be resulting the RTS packet at the same instant of time. But one particular node will be retransmitting the CTS packet, indicating that it is ready to accept the data, and that in the third interval of the time the data will be transmitted from the sender node. The basic disadvantage that is present in MECA protocol is that when the binary exponential backoff mechanism is used in the protocol, at times it will start the flow of data. So taking that disadvantage into consideration, the next introduced protocol is MACAW protocol, which stands for Media Access Protocol for Wireless LANs, and this was introduced in the year 1994. So every packet header that is being transmitted will have additional field carrying the current backoff counter value of the transmitting node, and whenever a node receives the packet that is transmitted, it will be copying that particular value into its own backoff counter. The figure in front is the example topology. So here we have totally 4 nodes, S1, S2 and R1 and R2. Let us consider both the nodes S1 and S2 keep generating a high volume of traffic. The node that first captures the channel will start transmitting the packet, and let us assume that node S1 started transmitting the data. The packets transmitted by the other node S2, which is in state of transmission, will get collided, and the node keeps incrementing its backoff window according to the algorithm DB algorithm discussed earlier. As a result, the probability of the node S2 to acquire the channel will keep on getting decreased, and over a period of time it will completely get blocked. To overcome this particular problem, the backoff algorithm has got modified in MACAW. And now how this particular MACAW was designed is, every packet header, every packet that is being transmitted, in its header will have an additional field that will carry the correct backoff counter value of the transmitting node, and every node receiving the packet will copy that value into its own backoff counter. So because of this particular technique, the bandwidth utilization would be very fair among all the nodes that are present in the network. But here another problem that is with respect to the binary exponential backoff algorithm is that it will adjust the backoff counter value very rapidly, both when a node is successfully transmitting the packet and when it will collide with the other node while the transmission is going on, and this will be detected by that particular node. So in order to avoid such large variations in the backoff values, a mechanism called as mild multiplicative increase and linear decrease backoff mechanism is used in MACAW. So what happens in this is, whenever a collision has occurred, the backoff value will be increased by a multiplicative factor which is equal to 1.5, and upon the successful transmission it will be decremented by 1. So because of this particular mechanism, it is capable of eliminating the contention, and hence the periods which are very long with respect to the contentions can be minimized. So the technique that is used here is MILD, which stands for multiplicative increase and linear decrease, and the factor by which it is increasing is equal to 1.5. In MACAW, another modification that is related to the backoff mechanism was made, and this is done by maintaining multiple queues at each and every node that are present in a network, one each for every data stream that has to be transmitted, and running the backoff algorithm independently for each queue that is present or made. And that particular node which is ready to transmit the data will first find out how long it has to wait before it could transmit an RTS packet to the destination node. And this will be made taking again into consideration the topmost packets that are in the node queue. Here again, but in MACAW protocol, the error recovery responsibility will be completely given to the data link layer. In the data link layer, the recovery process can be made easier and faster, as the timeout periods can be modified to match with respect to the physical medium that is deployed there. So in MACAW, after the successful transmission and reception of each data packet, the receiver node will transmit an acknowledgement packet. So here it is stated as ACK. So after the acknowledgement packet is received, if the sender does not receive the acknowledgement packet, it will reschedule again. It will reschedule the same data packet for transmission, which we generally call it as retransmission. And the back of counter is incremented if the acknowledgement packet is not received by the sender. So to explain this, we have the next figure here. So we have two topologies here. Let us first discuss about the first topology, in which we have four nodes S1, S2, R1 and R2. So when a transmission is going on between the nodes S1 and R1, node S2 is of course free to transmit the data. The RTS signals or the control signals being transmitted by the S2 will be of no use, and these RTS signals from S2 can be transmitted only when it will receive CTS from R2. But this also will not be possible, as CTS packets from R2 will get collided at S2 with the packets being transmitted by S1. Because of this, the back of counter at node S2 will go on get increased unnecessarily. So an exposer node should not be allowed to transmit the data. But an exposer node can hear only the RTS sent by the source node and will not be able to the CTS will not be able to hear the CTS sent by the receiver, and does not have any assurance whether the RTS and the CTS was made successfully. So in order to overcome this particular problem, MACAW has another small control packet being called as a DS packet, which stands for data sending packet. So before transmitting the actual data packet to the source node, the source node will be transmitting the DS packet. So the DS packet which is being transmitted will carry the information like the duration of the data packet transmission, which could be used by the exposer nodes for updating the information, such that the duration of the data packet transmission will be held there. And the second diagram what is there is MACAW protocol will make use of one more control packet called as RRTS, which stands for request to send. RTS generally stands for request to send. Another R is added there, which is request to send packet. In this example, if it is clearly observed, again has four nodes R1, R2, S1 and S2. So assume that transmission is going on between nodes S1 and R1. Here now the node S2 want to transmit data to node R2. But as R2 is a neighbor of R1, it will receive a CTS packet from node R1, and therefore it will change its transmission. So node S2 has no way to think about the contention periods during which it has to stop for the channel. So it will keep on trying incrementing its back of counter after each attempt has got failed. So the main reason for this problem is the lack of synchronization between different nodes at the source S2. So the concept of RRTS here came into scene. So here what happened is the receiver node R2 contends for the channel on behalf of node S2. So if the node R2 has received an RTS previously, and because of which it is not able to respond immediately because of the ongoing transmission between the node S1 and R1, the node R2 will wait for the next period of time and it will transmit RRTS packet. All the neighboring nodes that will hear RRTS packet are made to wait for the next couple of slots. So when the node source S2 receives RRTS from node R2, and it will transmit the regular RTS packet to node R2, the normal packet exchange will continue from this particular instant of time. So this is the packet exchange, how the packet exchange happens with respect to MACAW. Here when S will transmit RTS to both N1 and R, and actually as S want to transmit data to R will be retransmitting CTS to both its neighbors S and N2. Right? After the CTS is transmitted, yes, the node S, instead of simply transmitting the data, before transmitting the data, it will first transmit the DS control signal. After the control signal is transmitted, then the transmission of data will be done, after which acknowledgement will be received by the corresponding receiver. So the next classification of the protocols is FAMA protocol, which stands for Floor Acquisition Multiple Access Protocol. So these are based on the channel access discipline, which will have the concept of carrier sensing operation and a collision avoidance system between the transmitter and the initiated receiver of the packet. The floor acquisition mechanism will indicate the process of gaining control to have a control over the channel through which the data will be transmitted. At any given period of time, the control of the channel will be allotted to only one particular node, and that node will be given a guarantee to transmit one or more data packet to different destinations without having any collision of the data that has to be transmitted. And here the carrier sensing is done by the sender will be followed again by the same control packets which we are mentioning as earlier. They are RTS and CTS packets. So this will enable the protocol to perform an efficient mechanism as already discussed in the case of MESCA. So here there are two variants of FAMA protocol. One is RTS CTS exchange with no carrier sensing, which we are calling it as MECA as discussed earlier, and the second category is RTS CTS exchange with non-persistent carrier sensing, which is defined as FAMA NTR. FAMA NTR stands for FAMA non-persistent transmit request. So this is one of the categories of FAMA, and this will take into consideration the properties of both non-persistent carrier sensing along with the RTS CTS control packet information exchange. So before a packet is transmitted, here the transmitter which is there will first identify for the channel. If the channel is found busy, then the transmitter will wait for back off amount of time and will retry again. So if the channel is found free, it will transmit RTS, and that particular channel which will receive RTS will be sending CTS if it is idle. If the CTS is not received within the stipulated amount of time period, or if the CTS received is found to be corrupted, then the node will take a random back off period of time and will try again. Once the sender node receives CTS packet without any error or without any delay, it can start transmitting its data packet in the form of burst. And the burst that we are saying, which is in the form of again zeros and ones or pockets, whatever it is limited to a maximum number of data packets, after which the node that is transmitting the data will leave the channel and will make the other nodes to contain the channel to occupy the channel. So in order to allow the sender node to transmit the data, once it acquires, the receiver will be made to wait for an amount of time which is here designated as tau seconds. And after the tau seconds are processed, each data will be received. The tau here will indicate the maximum channel propagation time. Tau will denote the maximum channel propagation time, and a waiting period of 2 tau seconds will be given on a transmitting node after delivering any control packet that has to reach the receiver. So this is allowed, or this is done in order to make a convenience for the RTS CTS exchange without any errors. So the node that is transmitting an RTS is required to wait for 2 tau seconds after transmitting the RTS in order to make or receive the corresponding CTS from the receiver. So after transmitting the final data packet, the transmitting node again will be made to wait for tau seconds in order to allow the receiver which is there for the data packet to be received correctly.